Okay, so we will now talk about a new topic, which is kinetic energy. Kinetic energy is the energy associated with motion. So whenever an object is moving, it has kinetic energy. So what is the definition of kinetic energy? Suppose you have an object of mass m, let's say it's a car. The mass of the car is m, and it's moving with a velocity v. Then the kinetic energy of the car is going to be, the symbol for kinetic energy is k, it's going to be half mv square. What is the unit of kinetic energy? It's joules, which is exactly the same unit as the unit of work. And in just a little bit today, you will see that work and energy are pretty much the same thing. So it's not surprising that they have the same units. Okay. So that is the definition of kinetic energy. You can see that it depends very strongly on the velocity. It's proportional to the square of the velocity of an object, and it's only proportional linearly to the mass of an object. So kinetic energy depends very strongly on the velocity of an object. All right, so the next thing that we'll talk about is a very, very important theorem called the work kinetic energy theorem. Okay, what does the work kinetic energy theorem say? Suppose you have a car that has a certain velocity over here. So as a result of that velocity, let's say its kinetic energy is k initial, and then a bunch of forces act on the car. So what could these forces be? For example, there might be the force of the engine. There might also be a force, so this is the force of the engine. There might be a force of drag, air resistance, acting in the opposite direction. So anyway, under the influence of all of these forces, the car gets over here, and it has a different velocity over here. So it's got a different velocity, and as a result of that, it has a different kinetic energy, and its final kinetic energy is k. Notice that I have a certain convention for expressing initial and final quantities. When I put a zero subscript, that refers to initial, and if I put no subscript, that means final. So this just means initial. The zero subscript here means initial, and this without any subscript is final. I just like to do this better than writing k sub I and k sub f. So whenever you see a zero subscript, for me that means initial, and no subscript means final. All right, okay, so that's just a weird convention that I use. So the kinetic energy of the car has changed from k initial to k final, right, under the influence of a bunch of forces. Now, in the last lecture, we learned how to calculate the net force, right? So the net force is the total amount of work done by all the different forces. So the work kinetic energy theorem tells us that the net work done is equal to the change of kinetic energy. So the net work is the total amount of work done by all of these forces, all the different forces. So the net work, according to the work kinetic energy theorem, is going to be equal to the change of kinetic energy. And that is the statement of the work kinetic energy theorem. Okay, so let me illustrate the work kinetic energy theorem with a simple example. This example is pretty similar to the problem on slide 20. Okay, so basically what happens here is that you have a car that's moving with some initial velocity v0 to the right, and there might be a bunch of forces acting on the car. Predominantly, there are two forces acting on a car. One is the force due to the engine in the forward direction, and the other is the force due to air resistance. I'm combining those two forces as a net force acting in the forward direction. That's what the F net is. So the under the influence of F net, the car moves through a distance x. I think I'll just go with d rather than x. It moves through a distance d, and by the time it gets to the end of that distance, its velocity has gone up to v, right? V final. So its initial velocity was v initial, and its final velocity is v final, right? And the distance that it's covered is d. All right, so let's first calculate the acceleration of the car, right? So for this, you can just use the third kinematic equation. You know the final velocity and the initial velocity, you know the distance. So you have to find the acceleration of the car. So find acceleration of the car. So v final square is equal to v initial square plus 2a times the distance covered by the car. So this is just the third kinematic equation. And so from here you can just solve for a. A would be v square minus v0 square divided by 2d. All right. Next thing we can calculate is the net force on the car. So F net is equal to mass times acceleration, Newton's second law, right? So the net force would just be mass times the acceleration, which I can just rewrite what we just found here, v square minus v0 square divided by 2d. That is the F net. Now let's calculate the net work done. So the net work you can just find by, if you know what the net force is, you can just find the work done by the net force, and that would just be the net work. So net work is simply F net multiplied by the distance moved by the car, right? So that would just be mv square minus v0 square divided by 2d times d, which you can write as mv square minus mv0 square divided by 2, and that's w net. Now what did we just get here? You can rewrite this as half mv square minus half mv0 square. That's our w net. This is just k final. Half mv square is k, and this is just k initial. So you've just proved that the net work done is equal to the change of kinetic energy. And that's just a simple illustration of the work kinetic energy theorem. So slide 21 is fully worked out on the slide. Let's try a typical example using the work kinetic energy theorem, and that is the example on slide 22. So try this problem yourself. Pause the video and try this problem yourself. And if you have, and only after you've thought about it for a while, then restart the video and look at the solution. All right, so what is this problem saying? It's saying that there's a simple pendulum, which is, so simple pendulum, so this is slide 22. So a simple pendulum consists of a point mass, mass m, and a massless string of length L, and it's hanging vertically. The bob is given, so this mass is called the bob. So the bob is given a horizontal velocity v0, and as a result of that, the pendulum rises up. The string always remains taut. The pendulum rises up. The question is, how high will the pendulum, how high will the bob rise? The length of the pendulum is L, and you have to figure out how high does it rise. You have to figure out this height, h. Okay, so how do we do this problem? Well, let's apply the work kinetic energy theorem. There are multiple ways of doing this problem, but let's just apply the work kinetic energy theorem. So the net work done equals the change in kinetic energy, right? So let's think about the right-hand side of this equation first. What was the initial velocity So I can write this delta k as k final minus k initial, and notice that I'm using my notation. No subscript means final, zero subscript means initial. So the formula for kinetic energy is half mv square. So this is half mv final square minus half mv initial square, right? What is the final velocity of the bob when it reaches, and let's name these positions A and B so it's easy to refer to them. So what is the final velocity of the bob when it reaches position B? That should be 0 because the bob is at rest at B. So the final velocity is 0, so the final kinetic energy is 0. And the initial kinetic energy would be half m v0 square, where v0 has been provided in the problem, right? So our delta k is simply negative half mv square, v0 square. All right, now let's think about the net work done by all the different forces. What are all the forces acting on the bob? There are two forces acting on the bob. One is the force of gravity, which is going to be like this, mg, and the other one is the tension. So the tension is going to be act through the thread like this. These are the two forces acting on the bob, right? Now, the tension force does not do any work. Why is that? Think about it like this. The bob is following a circular path, right? What is the direction of the tension force? The tension force is radially inwards. So the tension force is always perpendicular to the direction in which the bob is moving. So at any instant, the bob is trying to move in the tangential direction, tangent to the circle. And so the tension force is in the radial direction, so it's perpendicular to the direction in which the bob is moving, right? So please make sure you understand this point. And so the tension force does not do any work. Work done by tension is 0. Why? Because the tension is always perpendicular to the displacement. And why would the work done be 0 if the force is perpendicular to the displacement? This should be obvious from the formula for work. Work is F dot D, which you can also write as F d cosine theta. If the force and the displacement make an angle of 90 degrees, then cosine of 90 degrees is 0. So as a result of that, work is 0 if theta is 90 degrees. So that is why the tension does not do any work over here, right? So we just need to figure out what is the work done by gravity. And I'll just redraw that diagram. So this was our bob, and it's following this arc of a circle. The two forces on it were mg acting down and tension acting upwards. So the question is, what is the work done by mg? Now, the formula for work that we learned, Ft cosine theta, only applies when the force is constant and the object is moving in a straight line. Now, in this case, the object is not moving in a straight line. So we don't really know how to calculate the work done by gravity because the object is really not moving in a straight line, right? The force of gravity is constant though, but the object is not moving in a straight line. So what can we do here? Well, one thing we can remember is that gravity is a conservative force. So if gravity is a conservative force, then the work done by gravity does not depend on the path taken by the object. So you can replace the actual path taken by the object, which is the circular arc, by fictitious path, which goes like this. The advantage of taking this fictitious path is that it's just easy for us to calculate the work. So what we are doing here is that since gravity is a conservative force, we can use any path to calculate the work. We don't necessarily have to use the actual path taken by the object because every path will give you the same answer. So that's why we replaced, so let's use the dashed path to find the work done by the gravity. So how do we do that? So let's call this A, B, and C. So as the object moves from A to B, what is the work done by gravity? The answer is 0. Why? Because A to B, the displacement would be perpendicular to, would be in the horizontal direction, which is perpendicular to the direction of gravity. So the work done by gravity would be 0. What about as you move from B to C? The work done by gravity in this case is going to be, all right, so in this case we will get a non-zero answer, so let's calculate that. The force, the formula for work is Ft cosine theta, right? So the force is mg, the displacement is the height h, which is bc. That's actually what we are looking for in this problem. And what is the direction between, what is the angle between the force and the displacement? Well, the force is downwards, the displacement is upwards. So the angle between them is 180 degrees. Cosine 180 degrees is -1. So work done by gravity is minus mgh, right? So the total amount of work done by gravity is equal to minus mgh. It's just obtained by adding up these two. And notice that I was able to calculate the work done by gravity because by using a fictitious path, which the particle did not actually follow, but we are allowed to use any path we want. So that's what we did here. All right, so let's plug all this into the work kinetic energy theorem. The work kinetic energy theorem says that the net work equals the change of kinetic energy. We've already found the change of kinetic energy earlier. That's minus half mv0 square. And the net work would be the work done by tension and plus the work done by gravity. So this one was 0, this one was minus mgh. So we get this equation minus mgh is equal to minus half mv0 square. And so from here we can just solve for h, which is h is equal to v0 square divided by 2g, which is the answer in this case. All right, so this was just an application of the work kinetic energy theorem. There are other ways of doing this problem. This is not necessarily the best way of doing this problem, but I just wanted to use this method to illustrate the work kinetic energy theorem. Okay, let's try the problem on the next slide. Okay, so I'll let you read this problem. So an object of mass m, it says that an object of mass m moves along the x-axis under the influence of a force which is given by minus kx. You should be able to recognize this force. It starts from rest at a certain position, x equals a, and find its speed at position x in terms of all these constants. All right, so let's give this problem a try. So this is slide 23. So we have an object of mass m moving along the x-axis, this force. So the object starts from over here, and the force is directed to the left because it's minus kx. And the initial, let's say this is the origin, so this is x equals 0. So the object starts from over here, x equals a. So the question is, what is the velocity of the object? And its velocity is 0. V initial is 0. What is the velocity of the object at some other x when it's over here? Well, one way you might think of doing this problem is the following. You might say that, okay, we have the force, so we could find the acceleration. How do you find the acceleration? So acceleration is equal to net force divided by the mass from Newton's second law. The net force would just be the force F, because that's the only force acting on it. So acceleration is force divided by mass, right? So it's minus kx divided by m. All right, so now you have the acceleration. You have the initial velocity, and you have to find the final velocity. Now, one mistake which I hope you would not even consider making is to use kinematics. So it's definitely not a good idea to use kinematics. It's incorrect to use kinematics here. Why? Because the kinematical equations only apply when the acceleration is constant. This is not a constant acceleration. It depends on x. So you cannot use the kinematic equations. Back in chapter, what chapter was it? 2 and 3, you notice that when you cannot use kinematics, you can still use the definitions of velocity and acceleration. So let's try that approach. So kinematic equations don't apply. So one thing you can do is, you could try this approach. Acceleration is defined as the derivative of the velocity. So to find the velocity, you might be able to integrate the acceleration, right? So that's a perfectly reasonable way of finding the velocity when the acceleration is not constant. So let's see if we can do that. Our A was minus kx over m dt, and we have to integrate this to find the velocity. We now have a problem. What is the problem? See if you can figure it out before you hear me say it. The problem is that we have a variable mismatch. We are integrating with respect to time, but we have an x here, right? So unless the x is specified as a function of time, so unless somebody provides x as a function of time, we cannot really go any further here. So at this point, we are stuck again. The first time we were stuck was when we tried to use kinematics and we realized that we can't use it. So we are stuck now. All right. Now, there is a way of getting around this problem. If you know your calculus really well, there are some math tricks you can use to get around this particular problem. But yeah, whenever you have a variable mismatch like this, I mean, inside the integral, if we had some function of time, that would be no problem. We could just go ahead and integrate. But since we have x, that is the main problem. So I hope the problem is clear to all of you, why we can't proceed further with this approach, right? So anyway, so this was a reasonable approach that we tried, and it didn't work. So let's see what we can do. We have a very powerful tool in our hands, and that is called the work kinetic energy theorem, right? So let's see if we can apply that. The work kinetic energy theorem says that the net work done by all the forces. So this is a new approach. The net work done by all forces is equal to the change of kinetic energy. So what is the change of kinetic energy? Let's work that out first. The change of kinetic energy would be the final kinetic energy, which is half mv squared, minus the initial kinetic energy, which is 0. So we are done with the right-hand side. The left-hand side, we have to calculate the net work done on the object by all the forces acting on it. There's only one force acting on it in the horizontal direction. That is the given force, f of x. So it's a variable force. So in the last video, we learned how to calculate the work done by variable forces. So you would integrate the force minus kx dx. You would integrate it from the starting position, which is x equals a, to the final position, which is x, just x, right? So let's go ahead and do this integral. You can pull out the minus k, which is a constant. The integral of x is x squared divided by 2, and you would plug in the limits a and x and that is going to be equal to half mv squared. So it looks like we are pretty much done with this problem. We just need to work out the left hand side and then isolate the v, and we are done. So the left hand side would be minus k x square, k over 2x square minus a square is equal to half mv square. You can just absorb the minus sign. You can just FOIL through with the minus k over 2, or just with the minus, and cancel out the 2 as well. So basically I'm just doing algebra. So v square is equal to k divided by m, a square minus x square, and then you have the answer. So v is equal to plus minus k divided by m, a square minus x square, and that's the answer. All right. So this was looked like a rather difficult problem in the beginning, because the standard tricks that we tried to use, like integrating the acceleration to find the velocity, would not work in this problem, because the acceleration was a function of position and not a explicit function of time. So we didn't know what that function of time was, how position depends on time. So we were not able to proceed with this approach. But we used the work kinetic energy theorem, and we had no problem working it out. So we got the answer right away. Let's think about this problem for a moment. What does it physically represent? So I'll just draw it over here. We talked about what F equals k negative kx, what force that represents. So basically what's happening over here is that this mass is connected to a spring, a stretched spring. Remember, a spring exerts a force given by F is equal to minus kx, and it's sitting on a frictionless surface. So it's sitting at the point, it's starting at the point x equals a, you just let it go from there. So the spring brings the mass back. Let's say that x equals 0 is over here, which is the unstretched point of the spring. And so when the mass gets back over here, the spring will not be stretched. But at that point, the mass has already acquired some velocity. So it will overshoot and go all the way over here to x equals minus a. And by that time, the spring will be completely compressed, and it will be pushing back. And so basically what this mass is going to do is that it's going to keep oscillating back and forth between x equals plus a and x equals minus a. This is a situation that you're going to see in chapter 14 in a couple of weeks. And this is the simple harmonic oscillator. And in fact, the formula that we just derived over here, this formula is going to be quite important in chapter 14, though we are going to derive it in a completely different, with a completely different approach at that time. Okay. So for now, this is just an exercise in applying the work kinetic energy theorem. So you don't have to worry about the simple harmonic oscillator for now. Okay, so going back to the PowerPoint, I have a very similar problem on slide 24. So please see if you can work this problem out yourself. It's very, very similar to the approach that to what we just did in this slide. Okay. Let's try this conceptual question. So if I remember correctly, this particular question on slide, what was the slide number? On slide 25 is an actual MCAT question. So see if you can figure it out yourself before you look at the answer. A crane lifts a 1000 kg steel beam off the ground and sets it down on scaffolding 100 meters off the ground. So you have a beam like this, and it's lifted up by a crane and placed somewhere over here maybe. So what is the net work done on the beam? So this is the beam. What is the net work done on the beam? Right? Now, if you apply the work kinetic energy theorem, the answer is immediately obvious. Net work done equals the change of kinetic energy. What was the initial kinetic energy of the beam? So that's K final minus K initial. The initial kinetic energy of the beam was 0 because it was at rest, and the final kinetic energy of the beam is also 0 because it's again at rest. So the change in kinetic energy is 0, And that tells you right away that the net work is equal to 0. So the correct answer is B. Now, you might be a bit surprised, like, how can the network be 0? Isn't something happening here, like the beam has been raised? Well, let's think about why the network is 0. So there are two forces acting on the beam. One is the force of the crane, which is in the upward direction, and the other is the force of gravity, which is in the downward direction. So which of these is doing positive work? The force of the crane obviously is doing positive work because it's getting its way. Right? The force is pulling upwards, the crane is moving upwards, the beam is moving upwards, and so the force of the crane is doing positive work. What about gravity? Gravity is doing negative work because the beam is moving up and gravity is pointing down, so gravity is not getting its way. So the total amount of work done by gravity and the crane force is 0 because they're equal amounts of work but opposite signs. All right. The next thing that we're going to talk about is potential energy. Okay. Suppose you have an object over here, and let's say that you apply a force on this. Let's say it's a heavy box, and you push on this box and make the box move from here to here. So you applied a force on this box F, and as a result of and let's say it's a rough surface. So as a result of your force, the box moved from here to here, and let's say that the amount of work done is 100 joules. Let's think about what this 100, how would you get this 100 joules? It would be force multiplied by distance in this case. So let's say that you do force multiplied by distance times cosine of 0, which is 1. So let's say that you do force multiplied by distance times cosine 0, and you calculated the work and it came to 100 joules. What is the significance of this 100 joules? Well, the force that you had to overcome was the force of friction, and the force of friction kind of looked like this. So you spent 100 joules of your own energy to overcome the friction and do work against friction, right? So what this 100 joules represents the transfer of energy from you. The energy was stored as chemical energy inside your body in the form of glycogen. You used ATP to convert that into energy, and that energy, that 100 joules of energy that you spent, went into overcoming friction and moving the object from its initial to its final position, right? All right, so this 100 joules represents the energy that you have spent in order to accomplish this. Now, suppose you are unhappy with what you have acquired with your 100 joules of energy. You have buyer's remorse, right? So is it possible for you to undo this? Like, can you just say that I want my 100 joules back? I'm not happy with it, with what I have accomplished. And let's just move the box back to where it was and go back to the way things were. And I just want my 100 joules back. The answer is no. The 100 joules that you've spent is impossible to recover anymore. What has happened to that 100 joules? You did work against friction, right? Friction is a dissipative force. So that work that you did against friction got converted into heat. So that would cause the floor to heat up somewhat, the bottom of the box to heat up. And ultimately, all this heat would be transferred to the air molecules in the room and it would just be gone. There's no possible way of getting it back. So when you do work against a non-conservative force, so here the non-conservative force was friction, the work done against friction is not recoverable, right? So when work is done against a non-conservative force, is not recoverable. It's gone. However, consider this situation. So that's an important property of non-conservative forces. The work done against a non-conservative force is converted to heat, and it's not possible to get it back. However, consider this situation. Suppose you have a similar box, and you raise this box up by a certain height h. So this height is h. So this time you just lift the box up and raise it to a height h, right? In this case, the force that you're overcoming, the force against which the work is being done by you, is gravitational force, right? And let's just, for simplicity, let's just assume that again you have done 100 joules of work. So the work done is 100 joules, but this time it went into overcoming gravity, which is a conservative force, rather than this friction force, which is non-conservative. So in this case, what's going to happen is that in this case, it is possible to recover the 100 joules of energy that you spent. How would you recover this 100 joules of energy? Well, it's not you won't get it back in exactly the same form that you spent it. So it's not possible to get it back as ATP back into your muscles. But there are multiple ways you can get this energy back in other forms. So the easiest way of getting this energy back would be, can you think of how you would get your energy back? Just pause the video for a moment and see if you can figure it out. Well, so again, the easiest way of getting that energy back would be to just drop the box, right? So you're holding the box up here at this height, just drop it. If you drop it, the box will start speeding as it comes down, and by the time it gets back to the ground, it will have 100 joules of kinetic energy, right? There are other ways you can get the energy back, like if the box is made up of metal and then you make it pass through a magnetic field, you can convert some of that energy into electric currents. So there's multiple ways you can get the energy back. But the point is that when you do work against a conservative force, work done against a conservative force is recoverable. So it's almost, it's like if you do work against a conservative force, it's like the energy that you're spending is stored. So this stored energy can be used later on, right? And converted into other forms of energy. So this stored energy is called potential energy. So potential energy can be thought of as work that's stored and can be converted into other forms of energy. And how do you get potential energy? You do work against a non-conservative force. You do work against a conservative force. And then the work that you're doing is stored, and you can get that, recover that work in the form of, in other types, in the form of energy later on. Okay. So what we just learned is summarized by this equation over here. And this is an extremely important equation. It's so important that I have it on a separate slide. I have one whole slide dedicated to this little equation. So the work done against a conservative force leads to a gain in potential energy. And the work done by a conservative force leads to a loss of potential energy. So that is what this equation is saying. So what we saw in the last example was that we did work against a conservative force, against the force of gravity, and that led to an increase of potential energy. Now, the second half of the story is that, suppose you drop the object from here, right? So if you drop the object will start moving downwards. Gravity will be doing positive work in that case, and potential energy will be going down, right? So when a conservative force, when work is done against a conservative force, the potential energy goes up. There is a gain of potential energy. This is what we saw with the box example. And when work is done by a conservative force, then there is a loss of potential energy. And that's what happens if you drop the box, and then the box had potential energy when it was at a certain height. And by the time it gets back to the bottom, it's lost that potential energy and it's all been converted to kinetic energy. So when the box is descending, as I just mentioned, okay, when the box, okay, let's look at when the box is ascending, then the potential energy goes up and gravity is doing positive work. So this is the final height of the box. Gravity is doing negative work in this case. And when the box is descending, then the potential energy goes down and gravity is doing positive work, right? So the relationship between the work done by a conservative force and the change of potential energy can be summarized by this very simple equation. The work done by a conservative force is negative of the change of potential energy. This is an extremely important equation which we are going to use several times in this course, and you'll also see it used a lot in physics too. Okay. All right, so please make sure you understand this equation. Okay, and then as an application of this equation, let's try the top hat question, the conceptual question on slide 28. So this question says that an electron moves horizontally towards a positively charged plate of a capacitor. Is it gaining or losing potential energy? So let's think about this question. You might say that this is physics 1, so why are we talking about physics 2 stuff? Well, the only thing that you need to know here is that the electrostatic force, which is the force of attraction between positive and negative charges, is a conservative force, just like gravity and the spring force. So that's all that you really need to know. So what's happening here is that you've got a charged particle, electron, negatively charged particle, and it's moving towards some positive charges. We've got a bunch of positive charges here, so there's a force of attraction. So the question is, and the electron is moving in the direction of the positive charges. So the question is that, is it gaining or losing potential energy? Well, here the conservative force, which is the electrostatic force, is it doing positive or negative work? Think about that for a moment. The electrostatic force is trying to take it to the right because it's a force of attraction, right? And the electron is moving to the right, which means that the electrostatic force is getting its way. So the work done by a conservative force is going to be positive. The relationship between the work done by a conservative force and the change of potential energy is given by this equation. There's just a relative negative sign. So if this is positive, delta U has to be negative. Okay? And so that means the potential energy of the electron is decreasing. So if the electron is moving from here to here, it will have a lower potential energy over here. Okay, so I hope this is clear. All right, so remember this equation that the work done by a conservative force and the change of potential energy have a relative negative sign. Okay, what we're going to do next is we're going to use this extremely important equation, WC is equal to minus delta U, to calculate potential energy in two very important scenarios. So we have we've learned about two conservative forces in this chapter, so far, and these are the only two that you're going to see in physics 1. And the two conservative forces that we've learned about are gravity and spring force. So these are the two conservative forces in physics 1. In physics 1601. So whenever you have a conservative force, there's a potential energy associated with it. So we're going to calculate the potential energy that's associated with each of these forces. So let's start with this potential energy associated with the spring force, which is also called spring potential energy. All right. So suppose you have a spring which is not compressed or expanded. So the spring is at its natural length, and we are just going to call this x equals 0 is the point where the end of the spring likes to be if it's not stretched or compressed, right? Suppose you stretch the spring or even compress the spring, it doesn't matter. So I'll just draw another one here. Suppose you stretch the spring to some arbitrary x, and this was the x equals 0. You've stretched out the spring to some arbitrary x. So in that case, you are increasing the potential energy of the system, right? Why? Because when you stretch the spring, you're doing work against the conservative force of the spring, right? The spring force is a conservative force. So you're doing work against that force. Whenever you do work against a conservative force, you increase the potential energy. So when you stretch a spring, the spring has potential energy. Okay? So basically, the work that you did and the energy that you spent in stretching the spring goes into the potential energy of the spring. So what we want to find out is what is the potential energy of a spring which has been stretched out to a distance x. Well, we can easily calculate the work done by the spring force as you stretch a spring. So we did this calculation in the last lecture, and you might remember that the answer was the work done by the spring force was negative half k x final square minus x initial square. We calculated this directly from the definition of work. So in this case, x final is just x, and x initial is 0. So that's the work done by the conservative force in this case, right? So let's say that the potential energy over here is 0. When the spring is not stretched, let's say its potential energy U is equal to 0. And I want to find out what is the U when the spring is stretched out to some distance x. That's what I'm after. So we are told that we know that Wc is equal to minus delta U, right? So that means Wc, which is, let's just plug everything into this equation, and then we can just solve for U final. So minus half kx squared is equal to minus delta U is U final minus U initial, which I'm just taking to be 0, right? So from here you get U is equal to half kx squared. And this is a very important formula. This gives you the potential energy of a spring that has stretched. And notice that exactly the same consideration would apply if the spring had been compressed. So I could also say compressed by an amount x. Okay, so that's our formula for spring potential energy. There is another calculation that we can do. We can also calculate the potential energy associated with gravity. Right? So that is called gravitational potential energy. So how do we calculate gravitational potential energy? We are going to use the same approach. Let's say that we have an object over here and it's lifted up over here, right? So if you're lifting an object, you're doing work against gravity. That's going to increase the potential energy. Let's say that potential energy here is 0. And we want to find out the potential energy at this point, and this point is at a height h above the ground, right? So we're basically setting the ground to be 0 height, h equals 0, and we want to find out what is the potential energy at a certain height. So how do we do that? Well, same equation, work done by a conservative force is negative of the change of potential energy. So the work done by the conservative force here is gravity, right? The object has mass m, let's say. So what is the work done by gravity? It's a constant force, object is moving in a straight line. So we can just use the simple formula for work, which is force, that's mg, multiplied by the distance, which is h, multiplied by the angle between the force and the displacement. The force is downwards. The force is always downwards, and the displacement is upwards, right? So the angle between the force and the displacement is 180 degrees. So this is going to be cosine of 180 degrees is equal to minus delta u. Cosine 180 degrees is -1, so minus mgh is equal to minus u final, which is u minus 0. And so from here you get u is equal to mgh. And that's the formula for gravitational potential energy. So if an object is lifted up by a height h, you're doing work against gravity, and so you're increasing the potential energy, and the amount that it increases is mgh. All right. Notice that this formula mgh, you're allowed to set h equals 0 wherever you want. So if you wanted, you could have set h equals 0 at the top as well. And so the potential energy at the top would have been 0, but the potential energy on the ground in that case would have been negative mgh. Since the difference of potential energy between 2 points is the only thing that matters, it doesn't matter where you choose h equals 0 for this particular formula. Okay. Now, the next thing that we're going to talk about, let's see. So we talked about all this. Okay. The next thing, we might as well just finish a little bit more before we end this lecture. So we've learned about kinetic energy and potential energy. The sum of kinetic and potential energy of an object is sometimes called the mechanical energy of the object. So the mechanical energy is defined as the sum of kinetic plus potential energy. Right? All right. Okay. Now we are going to do a very important calculation. So the mechanical energy is defined as kinetic energy plus potential energy of an object. Just a definition. Okay. Now let's say that there is a certain object and there's a bunch of different forces acting on our object. So maybe it's a little cart or something, or a box. And there's an external force acting. You're pushing on the box upwards. So that's one force. There is a force of friction in the opposite direction. There is a normal force this direction. There is gravity. So there's many different forces acting on the object. Let's classify. Okay, so let's write down the work kinetic energy theorem. So the work kinetic energy theorem, and let's say that all of these forces have resulted in moving the object from here to here. So there has been, so all of these forces have done some work, right? What does the work kinetic energy theorem tell us? It says that the net work done by all of these forces equals the change of kinetic energy of the object, right? So to find the work done by all of these forces, you would have to, or the net work, you would have to just calculate the work done by each one and then add them up, as we did in the example in the previous video. You just have to add them all up and get the total amount of work done, right? Now, let's, to facilitate calculating that, let's classify our forces into 3 different categories. So we're going to break up our forces into um, external forces, non-conservative forces, and conservative forces. So that's how we're going to classify our forces. Now, what is a conservative force? Remember that in physics 1, there are only going to be two conservative forces. So the only two conservative forces are spring and gravity. So what is the conservative force in this example? It's just the mg. What is the non-conservative force in this example? Non-conservative forces are always the forces of friction, air resistance, air drag, and all that. So the non-conservative force here is just the friction force. That leaves us with the force exerted by the external agent, that's you pulling on the system, right? So our external force would be F. What about Fn? Do we need to consider that? Fn does not do any work. Why? Because the object is moving along the surface and Fn is always perpendicular to the surface. The normal force, if you remember from chapter 4 and 5, is always perpendicular to the surface. So if a force is perpendicular to the displacement, it doesn't do any work. So Fn doesn't do any work and we don't need to even consider it. We are only considering the forces which do work because we will find the net work, right? So we can write down the net work in our work in kinetic energy theorem like this. It's the work done by external forces plus the work done by non-conservative forces plus the work done by conservative forces. And that would be equal to the change of kinetic energy, right? Okay. This is just the work kinetic energy theorem. So nothing new so far. Work KE theorem. And I've just classified the forces into three categories. That's all that I've done. All right. Now let's use the fact that WC is equal to minus delta U. So let's try to bring in potential energy, right? So if you do that, you get W external plus W non-conservative minus delta U is equal to delta K. And then you can move the delta U to the other side, and that gives you W external plus W non-conservative is equal to delta K plus delta U. All right, let's call this quantity W other. What does other mean? Other means any force that's not a conservative force. So it could be an external force, it could be a non-conservative force like friction or air resistance. Other means any force that is not a conservative force. So in that case, we can write this equation as W other equals delta K plus delta U. Okay. Which you can also write as K plus U is E mechanical, right? So you can, if you want, you can also write this as delta E mechanical. So our equation, work kinetic energy theorem, with all these little changes, becomes the work done by external and non-conservative forces equals the change in mechanical energy. What is that telling us? It's telling us that the mechanical energy of a system is only affected by the forces which are not conservative forces. So the external forces or the non-conservative forces, these are the only ones which can change the mechanical energy of the system. If all forces are conservative, so this is telling us that if all forces are conservative, then W other would be 0, right? Because W other is only the things that are forces that are not conservative. Then delta E mech is going to be 0. And so E mechanical would be conserved or constant because its change is 0. So if all the forces are conservative forces, then the total mechanical energy of the system would be conserved. In fact, that is the reason why gravity and spring force are called conservative forces. They conserve a certain quantity, which is called the mechanical energy of the system, right? So the mechanical energy of a system is only affected by forces which are not conservative, like the external forces and the um, non-conservative forces. All right. There is an alternative way of writing this equation. So the equation that we just got was delta W other is equal to delta K plus delta U. So I can write this as K, delta K I can write as K minus K initial. Delta U I can write as U minus U initial, U final minus U initial. That's equal to W other. Now I can just move the K initial and the U initial to the other side, right? And that would give me this equation. K initial plus U initial plus W other. I just move the K0 and the U0 to the other side and just flip sides. K0 plus U0 plus W other is equal to K final plus U final. This is an extremely, extremely important equation in this entire course. So one very, very important equation was Newton's second law, F net equals mass times acceleration. That is probably the most important equation in the course. And this is the second most important equation. So this equation is called the equation of conservation of energy. Conservation of energy. What's it telling us? And we've already seen what it tells us. We can also see it from this version, that K0, K plus U, this quantity is the mechanical energy of the system. So K0 plus U0 is the initial mechanical energy of the system. If you have external forces or non-conservative forces acting on the system, then they will change the mechanical energy of the system and you will get different K plus U. So external and non-conservative forces will change the mechanical energy of the system. If you have only conservative forces acting on the system, then K plus U will stay the same. K0 plus U0 will remain equal to K plus U, right? So in other words, energy of a system is always accounted for, right? So if a system has 20 joules of mechanical energy, if you do 5 joules of work, if an external force does 5 joules of work, that means 5 joules were transferred to the system, and so the new mechanical energy of the system will be 25 joules. If an external force does negative 3 joules of work, then 3 joules of work have been subtracted from the system, and so the new mechanical energy of the system would be 17 joules. So it's just saying that energy is always accounted for. It's really it's quite a simple, the physical content of this is quite simple. Okay. Now, so we talked about mechanical energy, we talked about this very important slide. So please make sure that you fully understand the last equation on this slide, because we're going to use this a lot. I would highly recommend working through the examples on, working through this little tutorial that I created on slides 34 and 35. These will sort of help cement the ideas in your mind. So please make sure that you work through each part of this. Okay, in the next video, we will, I think the rest of this PowerPoint, I just have a few examples of applying all these concepts. So in the next video, we'll look at a couple of examples of applying the conservation of energy equation, and that will conclude chapters 6 and 7. Okay.